When you peer across the rusted Martian surface through photos, you would be forgiven for thinking that Mars is a place of stillness. Flat, dusty landscapes seem to stretch out in all directions, with nothing but scatterings of rock and the faint whistling of the wind to keep at bay the almost oppressive solitude. But stay a while on this red world, and you will soon see a towering wall of dust and sand brewing on the horizon. You might think to yourself that this dust storm is similar to those we see on Earth, and have no idea that this storm is about to grow so large its thick dust will swallow up not just a region, not just a continent, but the entire planet. This all-enveloping superstorm arises on Mars usually every 3 Martian years, or about 5.5 Earth years. Its choking dust will blot out light for weeks, even months, and represents a huge challenge to the continued functionality of any technology that we put up there. If humans ever want to settle down on the red planet, it will be a hurdle we have to overcome. Which is a problem, as there is much about the origins of these storms that we still don't know. I'm Alex McColgan, and you're watching Astrum. Join with me today as we explore what we do know about the characteristics, mechanisms, and impacts of the Martian super dust storms, and what any humans would need to be aware of to make it through one. Mars didn't used to have to deal with planet-sized dust storms. Although Mars is now a barren, arid planet, it once had a thick atmosphere that was warm enough to support the existence of running water. However, over the course of the billions of years of Mars's existence, Mars dried out, and its atmosphere bled away until atmospheric volume was at less than 1% of what we have here on Earth. Those dust storms didn't just start happening because Mars became dry though. Although we don't understand everything about such storms' origins, we assume that a key component is Mars's temperature. With less atmosphere, in spite of Mars's high CO2 levels, Mars became far worse at retaining heat. When the surface starts to cool, there is no air to catch the escaping warmth. It is at the point where, if you were to stand on the planet's equator during its warmest time of the day, your feet might feel 23 degrees Celsius, while at your head, it would be 0 degrees Celsius. This means between day and night, Mars has some intense temperature swings. Temperatures there now range from highs of around 27 degrees Celsius down to a freezing minus 133 degrees Celsius at night. Temperature differences can cause winds to form, which can bring different weather systems across the planet. However, Mars's arid weather is no longer driven by rain and water cycles, but cycles of dust. Dust plays a surprisingly crucial role on Mars, and without it, those planet-spanning storms would likely never form. The atmosphere might be too thin to capture and transport heat, but the Martian dust, now that's another story. It all begins with that Martian dust getting into the air. There are a few mechanisms that make this happen. One is dust devils, of which Mars experiences thousands every year, usually during the Martian spring and summer. Warm rays from the sun heat the ground, causing the air directly next to it to rise, and cool air from the atmosphere to be drawn down to fill the vacuum. These contrasting winds create rising spirals of air that can end up hundreds of meters wide and 8.5 kilometers tall, although many are much smaller. Regardless of their size, as they meander their way across Mars's all-encompassing deserts, they suck up dust and hurl it up into the atmosphere, creating a haze of slightly darkened skies in their wake. This process is thought to contribute to a miasma of background dust that constantly lingers in Mars's atmosphere. While this is the flashiest way by which dust gets into the atmosphere, it's not the most prevalent. Far more common is the simple influence of wind moving across Mars's dusty surface, and a process known as saltation. Mars's dust is surprisingly difficult to get up into the air. Small particles have a lot of cohesion due to being slightly electrostatic, kind of like packing peanuts, so that they stick together, which means they need a certain amount of momentum to get them going. Oddly enough, larger particles are actually easier for the wind to get moving as they experience less cohesion. So, it's these larger sand grains that are lifted by gusts of wind and are moved for short distances. But because they are ultimately too heavy for the wind to suspend, they crash down again, and the force of these tiny impacts imparts enough momentum to overcome cohesion and get the lighter dust airborne. However, once it gets up there, Mars's lower gravity means that it's easy for dust to remain in Mars's atmosphere for a really long time, weeks or months. And this is enough to start driving the formation of storms. Because, unlike the thin air around them, particles of dust are really good at collecting heat from the sun. As the sun warms dust in the atmosphere, they act like little radiators, slowly releasing the gathered heat into the air around them where previously the warmth would have passed through the ground below. This makes the atmosphere nearby much warmer. Warm air rises, but now it begins doing so on a much larger scale than when forming the dust devils earlier. Wind has to be drawn in from the sides of the rising air mass, but this only adds more fuel to the fire. More wind means more saltation, and more dust being thrown into the atmosphere, and more opportunity for the atmosphere to warm. Eventually, this out-of-control process ramps up into a regional dust storm. The good news is that on a local scale, a dust storm on Mars is not very dangerous in and of itself. Wind speeds top out at 97 kilometers an hour, only half the speed of hurricane winds on Earth. And even this is misleading due to the thinness of the atmosphere. Even when it is traveling quickly, you wouldn't feel much. In the same way, a single person has less pushing power than a whole crowd. Despite what you might see in some science fiction stories based on Mars, dust storms are not powerful enough to push over spacecraft or break satellite dishes. However, such storms carry their own incidental dangers. It's very bad news for any Martian rover that relies on solar power to function if a dust storm filled with slightly sticky electrostatic dust particles suddenly passes overhead. Gradually, dust deposited from such storms is enough to block sunlight from reaching a rover's solar panels, which has spelled the end of more than one mission from Earth. But the problems magnify when you start scaling such storms to larger and larger sizes. Mars does not have a perfectly circular orbit. Every year, around the Martian southern hemisphere's spring and summer, the planet is at its closest to the Sun and, as a whole, is warmest. For reasons we don't fully understand, during this time of year, regional dust storms start merging into a superstorm the size of a continent. It's of course possible that several storms just happened to be forming anyway, and they started to merge just by proximity. Although their regularity makes it seem like coincidence is insufficient an explanation. After all, these happen yearly, like clockwork, once the temperature gets warm enough. Those are just the continent-sized ones. Scientists of yet do not have an explanation for the stage above that, the planet-sized storms. These occur once every 3 Martian years, which seems like a short enough timescale that you can rule out Milankovitch cycles as their origin. Those normally work on timescales of thousands to hundreds of thousands of years. Perhaps there is some aspect to the dust cycle that needs to restock, and it takes 3 Martian years, or around 5.5 Earth ones, to do so. We don't really know. While most dust storms on Mars last only a few days, these apex of storms can last for weeks. The impact of these storms can be profound for any human technology around the planet. Scientists can measure the availability of sunlight on Mars using aerosol optical depth, or AOD, to check how much sunlight is being absorbed or reflected by pollutants in the air. The AOD on Mars is usually around 0.5. For context, an AOD of less than 2 is needed before rovers like Opportunity or landers like InSight can charge their onboard batteries. The thick smoke caused by a wildfire on Earth that starts to turn day into night is an AOD of 7. These planet-sized dust storms hit AOD of 9 to 11. They represent a near total blockage of light. In 2018, a storm of this variety killed the Opportunity rover by swamping its solar panels and forcing it into hibernation mode. Without power running through its onboard heaters, the wildly oscillating day-night temperatures caused something critical to break in the rover, and it never woke up. These storms are a problem for other rovers too, even ones with onboard nuclear batteries like Curiosity. The clouds are thick enough to block communication to and from the surface, meaning scientists have little choice but to wait them out. But that's not all. Even satellites can be affected by these storms. The colossal amounts of warming dust in the air causes the entire atmosphere to expand, bringing some of it into the orbital paths of satellites. They have to burn precious fuel, making course corrections to ensure the atmospheric drag doesn't bring them crashing down out of the Martian sky. If you were a human hoping to settle on Mars, you'd need to find a way to overcome these issues. Solar-powered settlements would not survive such storms without another source of power, and humans don't do well at such freezing temperatures. Losing the ability to contact our satellites could also leave us isolated and vulnerable for those few weeks. People would need to have a certain degree of self-sufficiency, as if anything were to go wrong while a storm was blowing, you wouldn't be able to call for help. Still, in time, these storms prove to be their own destruction. Blocking so much light eventually means that the surface stops getting warmed enough to create the upswelling winds that lifts the dust into the air in the first place. Without more rising dust, these storms starve themselves and peter out. Quiet returns to the red planet. Things are still once more. Any rovers that survived can emerge from hibernation mode, ready to continue with their science now that communications with Earth have resumed. As of 2023, there are 3 rovers active on Mars: NASA's Curiosity and Perseverance, and China's Zhurong. Of the 3, Zhurong is the only one utilizing solar panels as a power source. It will have to be careful. The last superstorm was in 2018. Given that these occur on average every 5.5 years, the next one could be coming soon. A little wind will start blowing, some dust will start to stir, and the cycle will begin anew. Well everyone, here it is, your most asked for video. Titan. And to be fair, I can understand the curiosity towards it. It is the only moon with a substantial atmosphere. There's clear evidence of stable bodies of surface liquid on it. And best of all, mankind has visited it, so I will be able to show you a lot of real photos and video footage. I'm Alex McColgan and you're watching Astrum, and here is everything you could want to know about Saturn's biggest moon, Titan. But let's start from the beginning and give some context to this remarkable planet-like place. Titan is the 6th spherical moon from Saturn, and unlike Jupiter's 4 Galilean moons, in the Saturn system, Titan is all by itself in its size. The rest of Saturn's moons are pretty small in comparison. To give some idea of how big it is, Titan's diameter is 50% larger than Earth's moon and is 80% more massive. In fact, it's the 2nd largest moon in the entire solar system, after Jupiter's moon Ganymede. It does actually appear slightly bigger than Ganymede if you were to put them directly side by side, but this is caused by Titan's thick atmosphere, which extends its apparent diameter. Even so, Titan's real diameter is still larger than the smallest planet, Mercury, but it's only 40% as massive. As its density is quite low for its volume, its gravity is reasonably weak at only 0.14 Gs, or 1.35 meters per second squared, which is even less than our moon. Due to Titan's low density, it is thought that its composition is half water ice and half rocky material. Unlike other celestial objects this size, it is believed Titan has a differentiated interior. This means it has layers. And like a lot of other large moons, one of those layers is thought to be a liquid ocean comprised of water and ammonia under the moon's crust. This liquid ocean is comparable to Earth's magma layer, situated between the core and the crust, and has been made liquid due to heat, pressure, and to a certain degree, tidal forces. The existence of this liquid layer was proven more likely when Cassini, the spacecraft orbiting Saturn, discovered extremely low frequency radio waves in Titan's atmosphere. Titan's surface is not known to be a good reflector of low frequency radio waves, but the liquid interior would be. Another reason is that the surface features on the moon have shifted by up to 30 kilometers since Cassini started observations, which could imply that the surface is not attached to the core, but is rather floating on this liquid ocean layer. And while there is no evidence of life on Titan, scientists do speculate that the conditions would be right for there to be life in this subsurface ocean. Unfortunately, if there was life to be found on the surface or below, we'll have to wait a while, as there are no planned missions to check out this possibility, and Jupiter's Europa is a more likely candidate to be investigated for life in the foreseeable future. The differentiated interior of Titan does not produce a magnetic field. Titan is still quite protected from the solar wind though, as 95% of its orbit around Saturn is within Saturn's own magnetosphere. Titan orbits Saturn once every 15 days and 22 hours, and has a rather large orbital eccentricity, which means the orbit isn't so circular. Its orbital plane is also at an angle, but that doesn't mean that Titan is likely a captured object. Rather, like Jupiter's Galilean moons, it is thought that Saturn also had several large moons in the past, but most of these had been destroyed through big collisions, which left Titan the lone victor. Saturn's medium-sized moons, like Iapetus and Rhea, are thought to be the remnants of this tumultuous beginning. Titan's day, like the day on our moon, is identical in length to its orbital period. This means Titan's rotation is tidally locked to Saturn, and only ever shows one face to the planet. Not that visually it makes any difference. Titan's hazy atmosphere completely blocks the view of the surface from an outside perspective. On the other hand, you might just be able to see Saturn while standing on Titan, although the view would be significantly obscured. This does mean, however, that if you were to stand on one spot on Titan, Saturn would never move in the sky. Removing Titan's haze, this is what it would look like. This leads us on to one of the topics that truly sets Titan apart from the rest of the moons in the entire solar system, its substantial atmosphere. I remember the first time I ever saw a photo of Titan, I was truly blown away, as it never occurred to my young self that the moon could even have an atmosphere. I thought it must have been a new planet they'd discovered recently or something. To me, what looks odd about the atmosphere is how far it stretches into space. When you see a picture of Earth, you see that the atmosphere has quite a tight fit around the planet. Titan, on the other hand, looks like it has a thick blanket all over it. There are a number of reasons for this. The first one is that Titan is a lot smaller than Earth, but its atmosphere is 1.9 times more massive than Earth's, or 7.3 times more massive on a per surface area basis. The second reason is that Titan's gravity is a lot weaker than Earth's, meaning it doesn't pull it down as strongly. The mass of the atmosphere actually means the pressure at the surface is 1.45 atmospheres, or 45% more than the atmospheric surface pressure on Earth. And comparing the two, you can see the extent of how far Titan's atmosphere stretches into space. 600 kilometers high is only the limit of the mesosphere. Earth's mesosphere, on the other hand, stops at 120 kilometers. Even at a distance of 975 kilometers, the Cassini spacecraft had to make adjustments to maintain a stable orbit against atmospheric drag when it made its closest approach. Like Venus, Titan is a super rotator, meaning its atmosphere rotates faster than the rotation of the planet. This can especially be seen at the poles on the moon. Each pole has a polar vortex that rotates once every 9 hours, compared to the moon's rotation of 16 days. The vortexes on each pole seem to be like permanent hurricanes. So what does the atmosphere consist of, and why is it orange in colour? Well, the atmosphere is 98.4% nitrogen, the remainder being mainly methane and small amounts of hydrogen. There are also trace amounts of hydrocarbons from the breakup of methane in the upper atmosphere due to UV light, and it is these hydrocarbons that are thought to give Titan its orange hue. This constant breakup of methane to hydrocarbons should have meant the moon ran out of methane within 50 million years, a very short space of time compared to the age of the solar system. This means there must be a source that replenishes the methane, the most likely candidate being cryovolcanoes, although biological life has not been ruled out. The methane in the atmosphere creates a greenhouse effect, without which the temperature on Titan would be a lot lower. Conversely, however, the haze also reflects a lot of the sunlight, creating an anti-greenhouse effect, which cancels out some of the potential greenhouse effect from the methane. Now, while Titan's upper atmosphere gets 1% of the sunlight Earth does due to the distance from Titan to the Sun, another result of this reflection of sunlight means the surface of Titan only gets about 0.1% in the end. The Huygens team liken the difficulty of taking photos at this light level to taking pictures of an asphalt parking lot at dusk. All these things combined means that while it would be dark, a human would only need an oxygen mask and to wrap up extremely warm to be comfortable while standing on the surface of Titan. It really is cold on Titan, minus 180 degrees centigrade on average. This means any water on Titan remains solid and doesn't ever melt, evaporate, or sublime. Then why are there sometimes clouds on Titan? Well, these are not water ice clouds, but rather methane clouds, which means yes, it can rain methane on Titan. In fact, the temperature on Titan is just right for methane to be liquid. Methane freezes at minus 182.5 degrees centigrade and boils at minus 161.5 degrees centigrade. The temperature, combined with the surface pressure, got scientists very excited at the prospect of there being hydrocarbon lakes or seas on the surface of Titan, similar to water lakes and seas on Earth. If there really were lakes on this moon, it would be the first time this had ever been observed outside of Earth. This was actually one of the main driving forces behind Cassini-Huygens, to see what there was under that thick atmosphere. The Huygens probe, named after the astronomer who discovered Titan in 1655, was designed to enter Titan's atmosphere and land on the surface. The possibility of even landing on an ocean was taken into account during its design process. As the probe descended, its parachute was pulled, and after an almost 3-hour journey, it finally rested on the solid surface of Titan. Sadly, it wasn't able to see any lakes, but what it did see confirmed that methane lakes once existed, as Huygens landed on what appeared to be a dried up lake bed. These stones you see from the surface photos are rounded stones, much like pebbles found in a river or a lake on Earth. Cassini, from the perspective of space, was able to confirm that methane lakes are still found on Titan today. Near the South Pole, Cassini observed an area which was later confirmed to be a lake called Ontario Lacus. It is 20% smaller than its North American namesake, Lake Ontario. So in other words, it is still pretty big at 15,000 square kilometers. On this side of the lake, you can see a smooth shoreline eroded by waves. On the west side, you can see the first evidence of a river and delta on Titan, meaning that liquid hydrocarbons flow down higher plains to the lake, leaving delta deposits in much the same process you would find on Earth. Ontario Lacus is extremely shallow, only estimated to be between 40 centimeters and 3 meters deep, the deepest point likely to be just over 7 meters. As Cassini's radar mapped this lake, it found that the lake did not have waves bigger than 3 millimeters, meaning the surface would appear like a sheet of glass or a mirror. This doesn't mean there can't be bigger waves, unless this liquid is particularly viscous, but the likelihood is that it was simply not a windy day as the observations were taken. The atmospheric density and gravity on Titan should mean that waves would be bigger on Titan than they would be on Earth. As the north pole of the moon began to come out of a 15-year winter, another lake was discovered, Jingpo Lacus. As Cassini was passing by the moon, sunlight was reflected off the surface of Jingpo Lacus like a mirror, directly into the view of Cassini. Upon further observation, Cassini was able to detect further evidence of moving liquid on Titan, as can be seen by these rivers flowing into the lake. The second biggest lake on Titan to be discovered is Ligeia Mare. Found in the north polar region of Titan, it is bigger than Lake Superior on Earth, with a surface area of 126,000 square kilometers. While parts of this lake are reasonably shallow, the average depth is a lot deeper than Ontario Lacus at 50 meters, and some parts of it could reach depths of over 200 meters. Plenty of rivers can be seen flowing into the lake, and there are large islands found around this area here. A particularly curious observation Cassini made, dubbed the Magic Island, is the appearance and disappearance of what appears to be an island. Although scientists are unsure exactly what happened here, the theories are that it could be silt suspended in the lake, bubbles, or subsurface ice rising to the surface as the lake warmed during the moon's spring. But still very curious. The largest lake on Titan, at 400,000 square kilometers, is the Kraken Mare. As you can see, the lake is split up into two main parts, separated by a small stretch quite similar to Earth's Strait of Gibraltar. Its nickname is the Throat of the Kraken. Because of tidal forces and the size of the lake, it's thought the tide changes by about 1 meter, and so this strait may have strong currents and even whirlpools. The Kraken Mare is also quite deep in comparison to Ontario Lacus, but isn't any deeper than 170 meters. So, we know about the lakes on Titan now, but what other interesting surface features might it have? Well, plenty actually. Titan's surface is quite young as 100 million years old, which means its surface must be geologically active. Some scientists believe the dirty ice crust is substantially rigid, although there is some evidence to suggest that there is tectonic activity on the moon, possibly caused by tidal forces with Saturn. The main factor of a renewed surface, however, is likely to be the same thing that produces methane in the atmosphere: cryovolcanoes. Now this is pretty interesting. You know how magma on Earth is pretty hot, but when it comes out of the ground it freezes. Well, Titan has the same thing, except its magma is water and ammonia, and when it comes out of the cryovolcanoes and spills over the land, it too freezes to renew the surface. Because a water and ammonia blend is a lot less viscous than lava, it flows further than lava on Earth. This means mountains are more flat and will never reach the heights of volcanoes on Earth. While it is hard to confirm specific cryovolcanoes on Titan due to the obstruction caused by the atmosphere, the most likely candidate is Sotra Patera, found on the southern hemisphere. In this image, height has been exaggerated by a factor of 10, but it gives a good idea of the sides of the dome and the 1.7 kilometer deep pit, the largest that we know of on Titan. The force necessary for this to erupt would have had to have been incredible, and while it doesn't appear to be active now, it is being actively monitored. The fact that lava on Titan is a mix of water and other minerals means the surface could be compared to dirty ice. Because we know the Huygens bounced and wobbled in a certain way as it landed on Titan, we have a rough idea of what the consistency of the surface could be like. Scientists have referred to it as a soft, damp sand. Another theory is that it's like snow with a thin crust on top. Imagine walking on frozen snow. If you're careful, you can walk on a solid surface, but if you stomp too hard, you will sink in quite deeply. And Titan's believed to be something like this. Titan's highest mountains come in the form of ridge belts, like the Rockies in America. These ridge belts could also be a form of cryovolcanoes. The largest mountain on Titan can be found in one of these mountain ranges, known as Mithrim Mons, and is 3,337 meters high. Interestingly, mountains this tall are thought to be topped with methane snow. Also found on Titan are many gorges, valleys and dunes. Using infrared cameras to see the surface from space, what can also be seen quite prominently are these large patches of dark terrain. Originally, these dark patches were thought to be seas until the Huygens probe landed on one of those areas, known as Shangri-La. They could well have been seas in the past, but now they are plains of dark mineral deposits, similar to the Namib Desert on Earth, where they appear as windswept dunes in some places. Overall, Titan can be compared to Earth in lots of ways. Scientists think that Titan shows signs of what early Earth could have been like, only much colder. It's fair to say that Titan is remarkably interesting, and I can only hope it gets its own mission one day. Cassini has done a great job, but it was never a Titan orbiter, and its mission will soon be over anyway. What I would find extremely fascinating is to explore more of its surface, and hopefully it won't be long until a mission to do that will be approved. Until then, here was everything you could want to know about Titan. The Sun is a giant, bright celestial object of intense nuclear energy. It unleashes billions of tons of electromagnetically charged plasma hurtling into space every day. These violent eruptions, called coronal mass ejections, or CMEs, shoot off into the solar system, causing what we know as solar storms. These highly charged plasma particles race towards Earth at over 1 million kilometers an hour. And one might think that with the speed and intensity of these particles, we should all head for the bunkers when they arrive. However, the Earth has natural protections in place to prevent most of these particles from hitting us. One such protection is the Earth's powerful magnetic field, which pushes the particles around the planet and to its poles. Particles that do hit the atmosphere are absorbed and provide the energy to drive the climate on our planet. In fact, the Sun is crucial to life on Earth. For example, it provides just the right amount of warmth and light so that plants can photosynthesize the sun's energy to usable carbohydrates. This energy makes its way down the food chain until it reaches us, humans. We eat and convert food to give us energy that our bodies can use. Almost all food energy can be traced back to the sun, our life giver, and the very beginning of our food chain. But could the solar system's giant also create catastrophe? How big can these CMEs get? What if the largest solar storm of all time was to hit Earth tomorrow? Could the sun actually damage or destroy humanity? For a star, our Sun is relatively stable, a type of star informally known as a yellow dwarf. It is middle-aged and has not changed dramatically for the last 4 billion years. We can be glad our Sun is as stable as it is, as unlike most other stars, the energy it emits is fairly constant. If you were to look at footage of the Sun taken by the Solar Dynamics Observatory, however, you would quickly realize that even one of the most stable types of star has a landscape of activity. Sunspots, solar flares, and coronal loops are present every single day on the sun's surface. Could say the surface almost appears to be fluid, but the sun is neither solid, liquid, or gas. It is rather a giant, nearly perfect sphere of plasma. It is composed of mainly hydrogen and helium, and at the center of the sun, due to its enormous mass, nuclear fusion takes place. At the sun's core, hydrogen atoms are fused together under immense pressure to become helium.
The sun itself, I tend to think of it as an onion. It's really consisting of different layers. So in the core, the very center of the sun, essentially that's where nuclear fusion happens. Now you have to think, so essentially the sun is a kind of huge ball of plasma, soup of particles, ions, atoms, electrons, sort of everything mixed up together. On average, it takes a photon to travel through the radiator zone something like 170,000 years. It's basically it's that dense.
And then from that, it then hits the convective zone. So everybody knows that hot air rises and cold air falls. So what then happens is the material is very hot at the bottom near that radiator zone, and then it expands and it rises to the surface, and that's the main transfer of heat from that point onwards. Obviously then glowing from the surface like any hotter material does.
Plasma is an extremely good conductor of electricity and is also affected strongly by magnetic fields.
So sunspots are actually the surface representation of the magnetic fields of the sun. So the magnetic fields actually get very tangled below the surface. So between that radiative zone and the convective zone, the magnetic fields get tangled.
They tend to appear in pairs, in groups. If you think sort of a magnet, you have positive polarity, negative polarity. That's sort of normally what we see in sort of in sunspot pair. One would be positive, the other would be negative. And normally the strongest magnetic fields that we observe are in the sunspots.
The sunspots can be anywhere from about 15 kilometers in size to around about 160,000 kilometers, so multiple times the size of the Earth.
Sunspots can often be seen at the base of various solar phenomena. Coronal loops, large rings in the sun's atmosphere, prominences, large, bright, gaseous features extending outward from the sun's surface, reaching into space for thousands of kilometers. And solar flares, a sharp increase in the sun's brightness and temperature.
Solar flares tend to happen over active regions, and active regions are essentially as sunspot groups. So these are the locations where we definitely see the strongest flares.
So a reconnection event is essentially what produces the energy that causes both flares and CMEs.
Because the convective zone is very turbulent, many of the sort of current simulations show that most of the magnetic field, as it rises through the convective zone, is basically being destroyed, being diffused around. It's more complicated magnetic structures, such like twisted magnetic fields, that tend to survive. And so you can imagine, especially sort of over large sunspot groups, we do see very complex magnetic field configurations, magnetic fields, twisted, wreathed, basically creating these complicated geometrical topological structures. And it's within that structures that magnetic field, the magnetic energy is stored. And what happens during reconnection? I tend to describe it, think of the magnetic field as a rubber band. So you twist it, turn it, and then basically at some point you pull it too strongly and it breaks. And that's essentially when we have the reconnection event. And what happens during the reconnection event? Essentially, as the name suggests, the magnetic field lines reconnect.
And when that happens, you get a lot of energy being released. I mean, of the order of millions of nuclear weapons, nuclear bombs, all in one instant. And that energy will produce both solar flares, where large amounts of radiation is released, and also potentially lead to large-scale movement of the material that was suspended in the prominences, both towards the sun and away from the sun. When that reconnection event happens, then again, the material which is suspended in those magnetic fields normally will move one way or the other. A lot of it will move back towards the sun, often following those magnetic field lines, so moving to the footprints, like for instance, move to the sunspots, if that's where the footprints are. But equally, in the middle of those magnetic fields, quite often a bubble of material is essentially ejected away from the sun. And so what you'll end up having is millions of tons of charged material flying out from the sun relatively fast. I mean, of the order of hundreds of kilometers per second to thousands of kilometers per second. And those are what we call CMEs, coronal mass ejections.
These CMEs come in contact with the planets all the time. Venus, when faced with a CME, has its lighter particles stripped away in the higher reaches of the atmosphere by the force of the ejection. This leaves the planet with just the heavier molecules, a toxic smog that cannot, as far as we know, sustain any life. Earth would have a similar fate if it wasn't for its relatively strong magnetic field. Particles from a CME aimed at Earth are redirected around the planet because of the Earth's magnetosphere. Some particles get redirected to the Earth's poles, where the charged particles hit the Earth's ionosphere, causing beautiful aurora. Thanks to a combination of the Earth's magnetosphere and atmosphere, we are totally protected from all sorts of particles space likes to throw around. Or are we? When the Earth is hit by a CME, this is called a geomagnetic or a solar storm. When a solar storm hits us, Earth's magnetic field gets somewhat compressed by the force of the CME for the duration of the storm. Normally this wouldn't and hasn't been a problem for people with their feet firmly on land. But what would happen if the most powerful solar storm ever recorded was to hit Earth today? To find out what is believed to be the most powerful CME in recorded history, we have to go back to 1859 to a solar storm known as the Carrington event. From the 28th of August to the 2nd of September 1859, many sunspots appeared on the sun in one place. On the 29th of August, southern aurora were visible as far south as Queensland, Australia, which implies a solar storm was occurring. Before midday on the 1st of September, amateur astronomers Richard Carrington, who the event was named after, and Richard Hodgson separately saw and recorded an extremely bright solar flare. Carrington and Hodgson wrote reports independently, which were both later published in scientific journals. The flare was connected to a major coronal mass ejection that traveled directly towards Earth, taking 17.6 hours to make the 150 million kilometer journey, much faster than the speed of normal CMEs. Typically, a CME would take several days to reach Earth. It's thought that the high speed of this one was made possible by a prior CME, perhaps the cause of the large aurora event on the 29th of August in Australia, which would have cleared any ambient solar wind plasma for the Carrington event like a giant slipstream. With this slipstream in place,
the way was set for the biggest CME known to man. On the 1st to the 2nd of September 1859, the largest recorded geomagnetic storm occurred. Aurora was seen around the world, all across the northern hemisphere, as far south as the Caribbean. The aurora over the Rocky Mountains in the US was so bright that the green glow woke local gold miners, who began making breakfast as they believed it was morning. It was reported that because the aurora was so bright, people in the northeastern United States could still read a newspaper. The aurora was visible as far from the poles as sub-Sahara Africa, Mexico, Queensland, Cuba, Hawaii, and even at lower latitudes very close to the equator, such as in Colombia. This is unprecedented, as typically aurora aren't visible at the middle latitudes. By the 3rd of September, the aurora in the sky was said to be the brightest and most brilliant it had ever been. However, although beautiful, this storm brought unforeseen problems. A consequence of the geomagnetic storm was that the electrically charged particles from the sun surged telegraph systems all over Europe and North America, which caused them to fail, even in some cases giving the people that operated the telegraph equipment electric shocks. Telegraph pylons threw sparks from the charged atmosphere. Amazingly, some telegraph operators could still continue to send and receive messages even though they had disconnected their power supplies. The storm was comparable to a hemisphere-wide EMP bomb, fairly harmless to humans, but extremely bad for electronics. The force of the CME in 1859 was so strong that it compressed the magnetic field of Earth all the way down to its atmosphere. Due to the fact that North America and Europe were facing the sun at the time, these areas of the world were most affected from the initial cannonball of the CME. Looking back at geomagnetic storms since the 1850s, there have been a few which were big but not devastating. For example, in March 1989, a CME hit Earth, rendering satellites unusable for several hours and jamming radio stations in Europe. Power in Quebec was knocked out for about a day. Some people there incorrectly thought the Soviets were attacking, and the glow in the sky was the result of nuclear bombs. Thankfully though, this solar storm and many like it did no lasting permanent damage. Today, if a CME the size of the Carrington event or bigger was to hit Earth, the consequences would be far more disastrous than they were for mankind in the 1800s. Technology was only just picking up back then, whereas today we have satellites in space, computers, telecommunications, power plants that would all be severely damaged in such an event. Due to the range of a solar storm, it would greatly impact equipment over a large area, the most susceptible technologies being the electricity grid and telecommunications, which have cables stretched out over a large distance. Without proper safeguards in place, transformers on the power grid could break, and millions upon millions would be without power for a lengthy period of time. If transformers did get damaged, for example, it would take years to replace, as transformers take years to manufacture. Often, these transformers are tailor-made for the specific requirement and are not mass-produced. Without power, refrigerators would not be able to stop food from spoiling, and as the transport system would also be down as fuel stations require electricity to pump, replacing that food would be problematic. payment systems that rely on credit cards would not work. People would not have access to the internet as computers would not have power and battery-powered devices would run out quickly. Radio and TV stations would be disrupted. Hospitals would struggle when the backup generators ran out of fuel. We would be completely cut off from the outside world. The world is simply so dependent on technology, and especially on electricity, it is feared we have lost the ability to function as a society without it. And worryingly, it is our power grid that is most vulnerable to a super solar storm. An independent think tank recently put the cost of damages to the USA alone at $2.6 trillion, ultimately destroying the economy. And unfortunately, that does not cover the social impact it would have. As is often the case in natural disasters, some people would undoubtedly resort to more primeval instincts, with attitudes such as every man for himself. Chaos, looting, and disregard for the law could occur. This would only get worse the longer the population goes without hearing from their government or organization of authority. Hopefully, in such a situation, the good of mankind would prevail, but it is a possible scenario. The think tank placed the estimated recovery time to repair the damage of a CME at 4 to 10 years, and estimated that 2/3 of the US population could die of starvation, disease, and chaos during that time. We only need to look at a couple of examples to understand the severity of the situation. In 1989, Quebec experienced a large solar storm that made the power grid fail in just 90 seconds. This problem was exacerbated by the fact it was winter, where the temperature can drop well into the minuses, which left vulnerable people in a potentially bad situation. It took 9 hours to restore power, and total costs from the disruption were estimated to be around 2 billion Canadian dollars. From the social aspect, we only need to look at Puerto Rico, which is still without power for 40% of its population from the time of writing this script in early February. That means it has been without power for 140 days, and is estimated that it still needs 50,000 utility poles and roughly 10,000 kilometers of electricity cables. If a solar storm hits, it wouldn't just be an island that is rendered powerless, it would be an entire hemisphere. And Earth has had some very near misses. A Carrington-size event could have been a reality in 2012, where a huge CME was ejected from the Sun. This was the biggest CME that has been recorded with modern technology, and it directly hit one of the stereo satellites that was observing solar activity. It is the charged particles that cause this distortion effect shortly after this solar flare. And had it hit Earth, the hypothetical disaster scenario could have become a reality. Due to lack of historical evidence, we have no way to predict when the next big CME could hit Earth. As far as we know, a CME even bigger than the Carrington event could hit us tomorrow, or the next one could be in a few thousand years. But what mitigation plans does the world have in case of such an event? Since 1995, NASA have placed a telescope in orbit which is constantly monitoring the Sun for CMEs. As light travels much faster than the speed of a CME, it would roughly give us about 17 hours warning before the CME hit Earth. If everyone was acting fast enough, this might be enough time to turn off some of the power stations, thus protecting the electricity grids. This is called the Solar Shield Program, and astonishingly, the US is currently the only country to have such a program in place. Countries are also working on temporary transformers which are quicker to produce. Additionally, countries throughout the Western world are currently in the process of proposing upgrades to the power grids that would not allow a surge of electricity caused by a geomagnetic storm to destroy the network. This process, however, is slow and bogged down by bureaucracy. It seems countries are in no rush to foot the bill to upgrade the infrastructure. These measures to protect the power grid are not already in place worldwide. It also seems that most people in the world are not even aware of CMEs, but rather fear much less likely scenarios like an asteroid hitting Earth or aliens invading. Mankind as a whole is shockingly unprepared for a natural disaster caused by a super solar storm. George H. Baker, Professor Emeritus from James Madison University, spoke before the House Committee on National Security in the United States and gave this explanation for the reason progress is not getting made. He said, "To a major extent, the lack of progress in protecting our most critical infrastructure to solar storms is that the responsibility is distributed. There is no single point of responsibility to develop and implement a national protection plan. Nobody is in charge." When I asked the North American Electrical Reliability Corporation about EMP protection, they informed me, "We don't do EMP, that's a Department of Defense problem." The Department of Defense tells me EMP protection of the civilian infrastructure is a DHS responsibility. DHS explained to me that the responsibility for the electric power protection is within DOE, since they are the designated sector-specific agency for the energy infrastructure. And this is sadly from one of the most progressive countries in the world on the subject. And until mankind is prepared for a CME, we really are at the mercy of our life-giver star.
Venus is a beautiful, elegant planet, seemingly very calm and almost tranquil on the surface, wrapped in a soft cloud like a blanket. From an outsider's perspective, it's clear why it's named Venus, the Roman god of love. But go beneath the cloud layer and you'll find quite the opposite. Scorching temperatures, volcanism, and a crushing atmosphere are what you'd actually find on the surface. There are few places in our solar system more deadly, and its acid-laced environment makes visiting next to impossible. So, what do we know about this beautiful yet hellish planet? More than you might think. I'm Alex McColgan, and you're watching Astrum. Join me today as we delve into what makes this planet unique in our solar system. Get ready to find out everything you could want to know about Venus. Let's start by stepping back a bit to see where this planet fits into our solar system. Venus is the second planet from the Sun, and it's our closest neighbor. Its average orbital radius around the Sun is 0.72 astronomical units, or roughly 108 million kilometers. It doesn't vary much at all from this mean orbital radius, as it's the planet with the least eccentric orbit, orbiting in a nearly perfect circle. At Venus's closest approach to us, it is the closest of any other planet, being only 41 million kilometers away. Interestingly though, this is not when it's brightest in our sky, as when it's closest to us, we only see the night side, as it's between us and the Sun. It is still visible though, as the sunlight refracts through the atmosphere. It's actually brightest when it's a thinner crescent shape in the sky, and when this happens, it is the brightest object we see at night after the moon. As such, Venus is commonly misreported as an unidentified flying object. US President Jimmy Carter reported having seen a UFO in 1969, which later analysis suggested was probably Venus. Countless other people have mistaken Venus for something more exotic due to its startling brightness. I recently had the pleasure of looking at Venus through a telescope, and remarkably, the crescent shape of it was very visible. With Venus orbiting between us and the Sun, it may make you wonder if Venus ever eclipses the Sun from our viewpoint on Earth. And the answer is yes, but surprisingly very rarely. Transits happen in pairs, the pairs being 8 years apart, but every pair only happens once every 100 years or so. The last transit we had was in 2012, but if you didn't see that, I'm afraid the next one won't be until 2117. The reason for this rarity is because the orbiting plane of Venus is not exactly the same as Earth's. Also, Venus only catches up with Earth every 584 or so days. These two things combined ensure that, although a spectacular and predictable sight, it also means we'll probably only ever have the chance to see it once or twice in our lifetimes. All the planets orbit anti-clockwise around the Sun, and with this, Venus is no different. But unlike all the other planets, it rotates clockwise, or in other words, in a retrograde rotation. Not only that, but it has an extremely slow rotation, rotating once every 243 Earth days, slower than any other planet. This makes a sidereal day longer than a Venusian year, a Venusian year lasting 224 Earth days. A sidereal day, if you remember from my recent Mercury episode, which you can check out here if you missed it, is one rotation of the planet. Because of this retrograde rotation, however, a solar day, which is sunrise to sunrise, is considerably shorter, at 117 Earth days. This means you'd experience just less than 2 days on Venus in 1 year. To give you some perspective as to how slowly it rotates, at the equator, the planet is only rotating at 6.5 kilometers an hour. This slow rotation makes it the second most spherical object in the solar system after the Sun. It is unclear why Venus rotates backwards compared to the rest of the planets, but it could be due to a big impact with another object billions of years ago, or tidal locking with the Sun, or tidal effects on the Venusian atmosphere. Its mass and size are very similar to our Earth, hence why it's often referred to as our sister or twin planet. Venus is one of the 4 inner terrestrial planets, and it is a rocky planet. Its diameter is slightly smaller than Earth's at 12,100 kilometers compared to Earth's 12,740 kilometers, and its density is 5.3 grams per centimeter cubed compared to our 5.5 grams per centimeter cubed. This means the gravity on Venus is only a tenth weaker than that on Earth, surface gravity being 8.9 meters per second squared. But this is where the similarities end, because on the surface of Venus, the atmospheric pressure is 92 times greater than that on Earth. That's an equivalent of 1 kilometer under Earth's oceans. The reason for this is because the density of Venus's atmosphere is 93 times greater than Earth's. Fit that amount of gas into a space slightly smaller than what we have here on Earth, and you can understand why it's so densely packed. The atmosphere consists mainly of CO2 gas, and combined with sulfur dioxide clouds, you're left with the strongest greenhouse effect in the solar system, with temperatures of 462 degrees Celsius at the surface on average. This makes the surface temperature greater than Mercury's, even though Mercury is closer to the Sun, and Venus only gets 25% of the solar radiation that Mercury does. The difference is that Mercury doesn't have an atmosphere to retain the heat, whereas Venus certainly does. This means at nighttime, and even at the poles, the temperature remains fairly constant. Venus really is cooking. It absorbs so much heat, but like a thermal flask, it retains it and doesn't let much escape. With an axial tilt of only 3 degrees, it also means seasonal changes in temperature are also very minimal. Wind speeds aren't very high on Venus's surface, only being a couple of kilometers an hour. But because of the thickness of the atmosphere, it applies a strong force on the obstructions, moving small rocks and dust across the surface. On the other hand, wind speed at the cloud layer is much faster, reaching speeds of 300 kilometers per hour. These winds at the cloud tops circle the planet about every 4 to 5 Earth days, which makes the planet look like it's rotating a lot faster than it actually is. The cloud layer itself sits above the thick CO2 and consists mainly of sulfur dioxide and sulfuric acid droplets. Sulfuric acid, just as a side note, is highly corrosive, and this acid rain just adds to the hellish nature of Venus, although it does evaporate before it hits the surface. The clouds on Venus are highly reflective, only allowing about 10% of the sunlight through, and because they cover the entire planet, it obstructs a visual view of the surface from space. These clouds are also capable of producing lightning, much like on Earth, although it's not as common. Recently, it has been discovered that Venus has a large vortex at the South Pole, much like on Saturn. Now, Venus is the image on the left and Saturn on the right. They are shaped quite differently, and Venus only has one storm, whereas, incredibly, every single black dot in the Saturn image is a separate storm, with the main vortex being in the center. The vortex on Venus is at an altitude of 59 kilometers, which is just above the cloud deck. Which leads on to an interesting point about the atmosphere of Venus. Because at about 50 kilometers up, the air pressure and temperature would be tolerable by Earth standards. Even the gravity would feel very much like Earth. The only problem with a person actually being there is the air itself. But if you were to have an airtight plane or something like this, the conditions would actually be very Earth-like. Now, I want to head back down to the surface of Venus a little bit, as we actually have some real photos of the surface thanks to the pioneering efforts of the Russians back in the 60s to 80s. The probe Venera 7 in 1970 was the first probe to ever land on another planet and send back data. The previous attempts resulted in the probe's signal terminating before touchdown. Venera 7 probably fell over on impact, and so the only reading it gave was the temperature at the surface, which was 475 degrees Celsius. Venera 8 confirmed that at the surface the visibility was quite clear, with a visibility range of about 1 kilometer, as the cloud layers end at quite a high altitude, meaning it was suitable for cameras in future missions. Venera 9 sent back the first ever image of the surface of Venus. Venera 10, 13 and 14 over the course of 6 years sent back more imagery, this time in color, as well as a lot of data regarding the conditions of the planet. Since then, there have been a number of probes that have mapped out the surface of Venus. Using radar, they're able to see through the cloud cover and image the planet's surface in very high definition. The surface of Venus is dotted with a lot of big, but not necessarily active volcanoes. It has 167 volcanoes which are over 100 kilometers in diameter. The only complex of this size on Earth is the big island of Hawaii. This doesn't mean Venus is more volcanically active than Earth, but this is due to the fact that Venus has a much older crust than on Earth. Earth has plate tectonics, releasing heat and renewing the surface fairly regularly being at least 100 million years. Venus, on the other hand, doesn't have any plate tectonics. Instead, its crust is estimated to be about 300 to 600 million years old, when a global resurfacing event likely occurred. The theory is that the mantle under the surface heated up so much that it forced its way up through the crust, covering most of the surface with lava. An incredible 80% of Venus's surface is made up of cooled lava plains, and there are literally hundreds of thousands of volcanoes in one form or another. There are also 900 impact craters to be found on Venus, although none less than 3 kilometers in diameter. This is because anything smaller than 50 meters in diameter would fragment and burn up before it even hit the surface. And finally, let's have a look at the magnetosphere. Venus doesn't have its own magnetic field, which surprised everyone when it was first discovered, as Venus's composition is very similar to Earth's. But without more data, it's hard to say why this might be. Although a study in the journal Earth and Science Planetary Letters in 2017 suggested that perhaps it was to do with the absence of a massive impact in Venus's history. Earth had at least one massive impact. It's what formed the moon, and it's possible it played a part in kickstarting our magnetic dynamo. But Venus never had such an impact. Perhaps this explains the lack of a similar field. Regardless, as a result of this, solar and cosmic radiation interacts a lot with the upper atmosphere of the planet, producing lightning and an induced magnetosphere. Solar wind also strips off the low-density molecules out of the atmosphere, meaning Venus has a tail similar to a comet. Under certain conditions, this tail can tickle Earth when they are in conjunction with each other. Unfortunately though, this tail isn't visible with the naked eye. Sadly, we've come to the end of the video, but I'd just like to say thank you so much for watching this far. If you enjoyed it, I have a lot of other videos about our other planets which might be of interest to you as well, so be sure to check those out. Our solar system is filled with some truly incredible sights, and there's always more to discover. But for now, thanks for watching, and see you next time. Look up into a clear night sky with your naked eye, and what planets would you see? Technically, you would be able to see all of them at one time or another, all of them apart from Neptune. It is the smallest of the gas giants and also the furthest away, and it is a perplexing place. You would think a planet so far from the Sun wouldn't have a dynamic atmosphere that exhibits ginormous storms and super fast winds, and yet it does. So why is this planet as interesting as it is? I'm Alex McColgan and you're watching Astrum, and today we're going to delve into everything you could want to know about Neptune. Let's start right at the beginning. Neptune is the only planet found through mathematical prediction. You see, when Uranus was discovered and astronomers were plotting its orbit, they noticed that Uranus wasn't following their models. From the perturbed orbit of Uranus, Urbain Le Verrier in 1846 concluded that there must be another undiscovered planet, and he predicted where it should be. And remarkably, Johann Galle was able to find it only a degree away from the predicted point. Triton, Neptune's biggest moon, was discovered a few days later. But since then, Neptune has been poorly understood, as its distance from Earth and very small apparent size meant it couldn't be studied from ground-based telescopes very easily. It wasn't until 1989, when Voyager 2 arrived, that huge amounts of information about the planet became available. Suddenly, we could see what the planet looked like, confirmed that it had planetary rings, and discovered a lot of previously unknown moons. But let's get to today. What do we know about this planet now? Since Pluto's demotion to not a planet status, Neptune is the 8th and furthest planet from the Sun. It orbits at 30 astronomical units from the Sun on average, which means it's 30 times further than the Earth's orbit from the Sun. 30 astronomical units, in other words, is 4.5 billion kilometers. And from that, you can see why it would take a space probe, using current technology, 13 years to reach Neptune. 4.5 billion kilometers is a considerable distance. Because of this long orbit, it takes a huge 165 years to orbit the Sun once, which means we've only seen one Neptunian year since its discovery. This distance from the Sun means the average temperature in Neptune's atmosphere is very cold, minus 201 degrees Celsius. Its axial tilt is 28 degrees, meaning it's similar to Earth and Mars, which have 23 degrees and 25 degrees respectively. This means it has seasons similar to Earth and Mars too, the big difference being these 4 seasons last 40 Earth years each. At this moment in time, the Southern Hemisphere is experiencing spring. During this spring, the Southern Hemisphere receives more sunlight and appears brighter. This increase in brightness is actually quite noticeable, which is strange, as you would have thought that because the Sun is 900 times dimmer on Neptune than on Earth, from that distance it wouldn't make much of an impact. But even if it is only a small impact, it makes an impact nonetheless, and the increased sunlight levels in the southern hemisphere warm it up by about 10 degrees Celsius compared to the rest of the planet. This comparably higher temperature releases frozen methane into the stratosphere, causing its increased brightness, whereas elsewhere on the planet it remains frozen and stays deeper in the troposphere. Just a quick recap of the spheres of a planet. The troposphere is the lowest atmospheric level, followed by the stratosphere. Above those layers are the mesosphere, the thermosphere, and then the exosphere. But that's a very interesting topic in itself, and we'll save it for another video. If you look at the weather on Neptune, it actually has the fastest wind speed of any planet, with wind speeds blowing westward on the equator reaching a staggering 2,160 kilometers per hour, nearly a supersonic flow. And interestingly, most winds travel retrograde to the rotation of the planet. Bands are also formed on the planet, as well as colossal storms. When Voyager 2 passed by the planet in 1989, it saw the Great Dark Spot, a storm about the size of Earth passing through its atmosphere. Voyager also saw the smaller storm known as the Small Dark Spot, south of its big sibling. As Voyager 2 approached Neptune, this smaller storm changed in shade from dark to light. When Hubble was launched, astronomers were curious to see the fate of these storms, to see if they were a permanent feature like Jupiter's Great Red Spot. But when Hubble was pointed at Neptune in 1999, these storms had completely disappeared, and storms have come and gone ever since. Giant, bright, high-altitude clouds also come and go. But why then doesn't Uranus, which is very similar in composition and size to Neptune, also have such a blustery atmosphere? Don't get me wrong, wind speeds on Uranus are fast too, but it doesn't compete with Neptune at only 900 kilometers per hour. Can all this only be due to interactions with the Sun and its seasons? Something else must be at play here to explain the extremes in weather. The answer may lie deep beneath Neptune's surface. I mentioned that Neptune is the furthest planet from the Sun, so you would have thought it's also the coldest. But actually, Uranus is the coldest planet in our solar system. Neptune radiates heat from within, whereas Uranus radiates hardly any excess heat at all. This could be because a large Earth-sized body crashed into Uranus billions of years ago, which depleted all of its primordial heat. Astronomers now theorize that the more active weather on Neptune might be due, in part, to this higher internal heat. What is Neptune actually made of then? Its internal structure and atmosphere is thought to be very similar to Uranus. Its atmosphere is composed of mainly 80% hydrogen and then 19% helium, with very small amounts of methane. It's this methane though that gives Neptune its blue color, although it's a darker shade of blue compared to Uranus's cyan. Again, like Uranus, there is a liquid mantle of water, ammonia and methane ices surrounding the core. And where the core and the mantle meet, the pressure is so great that the methane may break apart and diamonds are formed under the pressure. Likely not diamonds as you or I know, but there could be a liquid carbon ocean with solid diamond bergs floating in it, and diamonds raining down through the mantle like hailstones. This is just a theory though, as technology has only recently started to recreate such pressures. Around the core of Neptune, it's thought to be 7 million bar, or 700 gigapascals, which is about 7 million times the pressure of Earth's atmosphere at the surface. Even the two ice giants' magnetospheres share similarities. Neptune's magnetic field is offset 47 degrees relative to its rotational axis. When Voyager 2 discovered this about Uranus, the first theory was that it had something to do with its unusual axial tilt. But then it found the same thing out about Neptune, which has a more normal axial tilt. So the current theory is that the magnetic field is either not generated in the core, but rather by an electrically conducting liquid mantle, or that the mantle deflects the magnetic field from the core, which gives it this weird offset in relation to its rotational axis. Every planet in the solar system hasn't actually got a perfectly aligned magnetic field. Even Earth's magnetic north is different from where the North Pole actually is. But it's only Uranus and Neptune that have such a tilted magnetosphere. Aurora do exist on Neptune too, but they are different from what you might expect, as they are extremely faint due to particles not getting as charge from the Sun, and because of the direction of the magnetosphere, they are mainly type B aurora, or SAR arcs. Earth gets these too, but they are not visible and you need scientific instruments to know that they are there. They could be stretching across the whole sky without you actually knowing about it. Another difference with the SAR arcs of Neptune is that they are not only found around the poles, but rather are around the mid-latitudes of the planet. Zooming out from Neptune a bit, we come to its ring system. Like all other gas giants, Neptune does have a ring system, although it is extremely faint as it is not as dense and is extremely dark in color. If you have these rings against the black backdrop of space and also have them be this far away from the Sun, then they are very hard to see. But there are 5 known rings in all, and they are named after people involved in the discovery and research of Neptune. The innermost is the Gale ring, which is very faint and very wide at 2,000 kilometers. Next is the first bright ring, Le Verrier. Although it's bright, it's only 113 kilometers wide. Next, and connected, is the Lasso ring, a very faint band 4,000 kilometers across. On the edge of this ring is the Arago ring. It is slightly brighter than the Lasso ring and less than 100 kilometers wide. Lastly is the outermost and the most researched ring, the Adams ring. It is only 35 kilometers wide, but is one of the brightest rings. It is particularly interesting as it is slightly inclined and has bright arcs in it. These arcs have been quite stable since they were discovered in 1980, but usually planetary rings are uniform throughout. These arcs must be material clumping and clustering up within the ring, but the reason for this is currently unknown. Lastly, I want to talk about the moons. Neptune has 14 known moons, which are named after water deities in Greek mythology. The most famous, and the largest by far, is the moon Triton, which actually contains most of the mass of all of Neptune's moons put together. I personally think it is one of the prettiest moons in our solar system, as it has amazing patterns and is burnt orange color. What is most interesting about Triton is the fact it orbits in retrograde, and also at an inclination to Neptune's rotation, which implies it is probably a captured object and not something that was formed alongside the planet. Triton might be the cause of the rings of Neptune, as it would have disrupted the orbits of moons, possibly causing them to collide and break up into what is now the rubble of the rings. Triton is even bigger than Pluto, and also has a tenuous atmosphere. Voyager 2 even saw faint clouds on its flyby of the moon. The next biggest moon is Proteus, which is a little irregular in its shape. Normally we only see this on smaller objects like asteroids, but Proteus is actually bigger, at 400 kilometers across, than the spherical moon of Saturn, Mimas. Why it is not a sphere is explained by past collisions of things hitting the moon, leaving these massive craters which you see. The inner, regular moons orbit around the rings, some acting as shepherd moons. The outer, irregular moons are all likely captured moons. Some of the irregular moons orbit prograde and others retrograde. The outermost moons of Neptune are Samathe and Netho, and are the furthest out satellite of any planet that we know of to date. They take a massive 25 years to orbit Neptune only once. This is because Neptune has a very large hill sphere, the hill sphere being the sphere in which the planet's gravity overcomes the gravity of the Sun. It has such a large hill sphere because it's already so far from the Sun. The Sun's gravity has less of an influence around Neptune than at the biggest planet, Jupiter. Well, thank you for watching. Did you learn something interesting about Neptune today? What mysteries would you like to see solved? We're still working our way through remastering the planets in our solar system series. What planet would you like to see us do next? Let us know in the comments below, and I'll see you next time. Tornadoes are devastating weather phenomena, but have you ever seen one traveling horizontally? Tornadoes are formed when opposing wind currents cause vortexes to form horizontally in storm clouds, which then shift their direction into a vertical spout of whirling air. But similar vortexes can happen on the edge of storm clouds too. When rising air from sources such as a coastal breeze meets falling air, like from a storm's downdraft, the resulting conflict sometimes twists the edge of the cloud into a spinning cigar shape, miles long, which can break away from its parent cloud entirely and rolls its way across the sky. These sideways twisters are called roll clouds. Don't worry if you see one though, they're not dangerous. In fact, in Australia, the Cape York Peninsula creates these 4 mornings out of 10 in October, and they are known as morning glories because of their stunning beauty. Be careful of the storm that follows them though. Hurricane Ian has proven to be a deadly one. It has claimed at least 86 lives, caused tens of billions in property damage, and cut out power to a quarter of Florida. It's the 2nd most damaging hurricane to hit the US on record, and the 5th strongest ever. But why was it so bad? Part of its strength lay in surprise. A day or so before it hit landfall, it was much weaker. However, in less than 24 hours, its wind speeds increased by over 35 miles per hour, bringing it up to the 155 mile per hour mark, a borderline Category 5 hurricane. This meant that many counties only issued evacuation orders a day before the hurricane hit, leaving people much less time to prepare for its sudden and astonishing 4.5 meter high storm surges. Rapid intensification of storms like this is linked to traveling over warmer ocean water, something we will likely see more of as ocean temperatures rise due to climate change. Although, let's hope there won't be a repeat for a while. Almost every planet in our solar system has an atmosphere. With atmospheres come weather, seasonal variations, and convection. Some of the most interesting atmospheric phenomena are cyclones, vortices, and storms. We are familiar with storms found on Earth, but most of them are relatively puny compared to the mammoths we have observed in other places around the solar system. So, what are the 10 most massive storms observed all over the solar system? This video is made in collaboration with Primal Space, who will be guest narrating for us today. For more really interesting space-related topics, be sure to check their channel out after the video. Primal Space, you're up.
Thanks. Number 10, Titan's polar vortices. Titan is an astonishing moon. It is unique in the solar system in that it is the only moon to have a substantial atmosphere. And it really is substantial. Titan is much smaller than Earth, and yet its atmosphere is 1.2 times the mass of Earth's. Because of this, Titan's atmosphere stretches far into space for hundreds of kilometers. In fact, its atmosphere at the surface is thick enough and the gravity low enough that flapping your arms on Titan with makeshift wings attached would allow you to fly. When Cassini made its closest approach over Titan in 2014, it blew by at an altitude of only 880 kilometers above Titan's surface. Even from this altitude, atmospheric drag from the flyby forced Cassini to use its thrusters to maintain its trajectory. In comparison, the ISS orbits Earth at an altitude of only 400 kilometers. Now, storms on Titan are not so easy to spot from space, but it's clear that methane clouds form and precipitation occurs regularly on this world. However, the most noticeable storm on Titan is the one found semi-permanently over its south pole. Titan is thought to be a superrotator, or in other words, its atmosphere rotates faster than its surface. And this is definitely the case with this vortex, which rotates once every 9 hours compared to the 16-day rotation period of Titan. Initial research suggests this vortex is related to seasonal variations on the moon, forming as the pole heads into its 15-year winter. Number 9, Mars cyclone. Mars is already pretty well known for its planet-wide dust storms, storms that kick up so much of Mars' ultrafine dust that it almost obscures the view of the surface from space. We've been able to observe these storms up from space with missions like Hubble, but also up close with the various rover missions on Mars' surface. These dust storms have ultimately been the reason why most solar-powered missions on Mars have ended. Most notably, in 2018, the Opportunity rover couldn't survive the dust storm that lasted several months. Mars' atmosphere is so thin, it's a wonder it can carry any dust at all. However, it just goes to show how fine the dust particles on Mars are, much smaller than Earth's sand grains. More surprising still was a discovery made in 1999 by Hubble, which observed a cyclone on Mars over 1,100 kilometers in diameter with a 200-kilometer wide eye. This isn't really the same as a hurricane on Earth, more like something known as a polar low. These are short-lived atmospheric low-pressure systems, like depressions, with a top speed not exceeding 100 kilometers per hour. Since that sighting in 1999, more have been seen in similar regions on Mars, never lasting for more than a day or two. Because of the whiteness of these clouds, it seems like they are dust-free, meaning they are likely water ice clouds. Number 8. Earth's cyclones. We have the best understanding of the processes behind storms on Earth, and we have plenty of different types here. However, as we focus on the biggest storms on record, we have to look at Typhoon Tip, a Category 5 super typhoon that formed in 1979 near Japan. This monster typhoon was comparable to half the land area of the US, at 2,200 kilometers in diameter. Its top sustained wind speed was an incredible 305 kilometers per hour, with a record low sea level pressure detected. Luckily, at its peak, it wasn't close to land, and by the time it did make landfall, wind speeds had reduced to 130 kilometers per hour. It was still enough to do damage, but it was nowhere near the deadliest cyclone on record. Number 7. Venus's polar vortices. Considering Venus can be our closest neighboring planet, it does seem to have been largely ignored by space agencies in the last few decades. However, Venus has the thickest atmosphere of any of the terrestrial planets, reaching 93 bar at the surface, the equivalent of being 900 meters underwater on Earth. Near the surface, the air flows slowly. However, tens of kilometers up, Venus's winds can be fast, around 400 kilometers per hour. This means that Venus is also a super-rotator. Venus does get lightning storms from time to time, but the really interesting storms are found around the poles again. Venus, like Titan, has polar vortices, but in the case of Venus, they are over both poles. These ones are also much larger, around the size of Europe. Found toward the center of these vortices are not one, but two eyes. This is quite unique, and the case for it is currently unknown. Space agencies have begun eyeing up Venus again recently, so hopefully it won't be too long before we get fresh data about this mysterious world. Number 6. Uranus's storms. A quick glance at a natural color image of Uranus doesn't seem to reveal much in the way of dynamic activity at all. In the infrared, that is a different story. Large bands span the planet, and active storms light up against the cooler surroundings. A high-contrast natural color view of Uranus from Hubble shows one of these storms, perhaps the biggest observed on Uranus, reaching 2/3 the size of the US. Uranus does seem to generally be a calmer place compared to Neptune, although this shows that giant storms are still possible here. This could be because Uranus doesn't seem to emanate heat as much as Neptune, meaning the engine driving such storms would not be as strong. Number 5. Jupiter's polar vortices. If you thought Venus was impressive with two eyes around its polar vortices, check out this amazing configuration of vortices found around the poles of Jupiter. Around the North Pole are 9 distinct vortices, kind of in a square shape, with a massive cyclone found in the center. On the other side of the planet, around the South Pole, we find a similar phenomenon, except this time there are 7 cyclones in a hexagon shape. Just one of these cyclones is bigger than the United States in diameter. In enhanced natural light, these vortices are beautiful. We don't know how permanent these features are. We've only discovered their existence since Juno arrived. If anything, we would expect them to merge, but they seem to be enduring. Nature certainly does like to throw us some curveballs from time to time. Number 4, Neptune's Great Dark Spot. As Voyager 2 flew by Neptune in 1989, we got very lucky. At just that moment in Neptune's existence, it was experiencing a massive storm that stretched out for 13,000 kilometers. Scientists thought they had just discovered a storm comparable to Jupiter's Great Red Spot, perhaps a permanent feature that had always been with Neptune. As such, they named it Neptune's Great Dark Spot. But when Hubble was launched and pointed at Neptune, the spot had completely disappeared. Since then, Neptune has had other dark spots come and go, although perhaps not as big as the one Voyager saw. All in all, it seems that Neptune spends about half its time with a dark spot. The rest of the time, these storms may continue on as less powerful cyclones, before finding renewed strength depending on Neptune's weather conditions. Number 3, Jupiter's Great Red Spot. It may surprise you to find out that Jupiter's red spot only made it to number 3 on this list. Although you should be aware that this storm is certainly no pushover, having existed since Galileo first spotted it back in 1665. During modern-day observations, this storm was, at its maximum, the equivalent of 3 Earths across. Although it is smaller today than it ever has been, it certainly won't go anywhere for another few decades at least. And as it continues to gobble up smaller storms, it could well be that it stays as a permanent feature. Wind speeds measure up to 430 kilometers around the walls. However, in the center, an eye can indeed be found. Here the air is relatively motionless, a stark contrast to what it's like in any direction for thousands of kilometers. Number 2, Saturn's storm. Saturn, like a lot of other planets with atmospheres, also has beautiful polar vortices, one found on each of its poles. Saturn's south pole has a relatively normal yet very large vortex and eye found in the center, with many smaller storms circling it. However, the really eye-catching storm is found in the North Pole, which has been dubbed Saturn's hexagon. In a similar fashion to Jupiter's hexagon structure of storms, Saturn goes a step further and exhibits an actual hexagon which stretches for 30,000 kilometers across. Each one of the sides of the hexagon about the size of Earth. The explanation for why this hexagon exists is not known for sure, but some experiments have recreated a hexagon in a circular tank of liquid by using just the right speed and gradient of flow. Cassini, as it passed by the central vortex, captured this stunning close-up of the cloud's structure found in the center. However, these storms did not put Saturn at number 2 on the list. The biggest storm on Saturn was named the Great White Spot. These are temporary storms which appear every few decades, the last one forming about 10 years ago. What makes these storms so big is that they are very long, sometimes even looping around the entire planet as they travel. They are thought to appear in conjunction with Saturnian seasons, forming as the atmosphere cools in a hemisphere. Leaving us with the biggest storm found in the solar system. Number 1, the Carrington Event. Solar storms are a near constant occurrence, with millions of tons of charged particles from the sun erupting into space. Coronal mass ejections, where charged matter that was suspended above the sun's limbs is ejected into space by magnetic reconnection events, are the sources of the most powerful storms. These storms affect the entire solar system, the effects of some being recorded all the way beyond Pluto with the New Horizons probe. And just like other storms we've talked about, not all solar storms are created equal. The biggest storm on record is the Carrington Event, the biggest coronal mass ejection to impact Earth back in 1859. The effects of it compressed Earth's magnetic field to its atmosphere, creating a near global aurora bright enough to read a newspaper at night. Had it happened today, it would have likely created major power outages across many countries, acting like a global EMP bomb. We were fortunate in 2013 as a Carrington-sized CME erupted from the Sun, thankfully, in the opposite direction from Earth. But as far as big storms go, the Sun is definitely the winner. Look at how small we are compared to some coronal loops suspended by the Sun's magnetic field. You may consider it cheeky to add solar storms to the list, but we couldn't resist, seeing as it has storm in its name. So there we have it, some of the biggest, weirdest, and most impressive storms found across our solar system. If you enjoyed this video and would like to watch more awesome space-related content, check out my channel, Primal Space.